Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 5 on modeling with linear functions. So for the last few lessons we've spent time remembering how to graph lines, realizing like what kind of parameters we can see in a linear function, like its slope and its y-intercept. We worked with linear functions in tables, and we even have done a few practical examples with linear functions. In this lesson, we are going to just concentrate on modeling real-world problems using linear functions. So let's get right into it in the first exercise. Now I will be using my my TI Inspire graphing calculator a bit. Mostly today though, I will be using it for just calculation purposes, not for any kind of graphing calculator purpose. So if you've got a calculator on your phone or a handheld scientific calculator, that should work pretty well too. But make sure to have something to do the longer calculations. Now, when we use equations to model real-world phenomena, we often first look to linear models, equations of lines, because honestly, they're the easiest to use and understand. All right, so let's talk a little bit about sort of some critical facts, linear modeling facts. So all linear models will have the form y equals mx plus b, where the two parameters are the slope, m, and the y-intercept, b. Now the slope m will always tell you how fast, or the rate at which the output is changing relative to the input. So you'll know slopes because you'll see things that have per units, miles per hour, dollars per brownie, things like that, okay? On the other hand, the y-intercept b always tells us how much we start with, right? It's the function's output or starting value when the input x or t or whatever is equal to 0. So let's take a look at exercise number 1 and do a little bit of linear modeling. Janine has $450 in her savings account at the beginning of the year. She places an additional $15 into her savings account at the end of each week. We want to model the amount of money that she has in savings, S, as a function of the number of weeks she has been saving, W. Letter A, fill out the table below for some of the number of weeks, just some of them. Show calculations that result in your answer. All right, so by the way, I know this thing's gonna be a linear function, right? Because I've got some kind of constant rate, $15 per week, right? So let's fill a little bit of this table out together, right? So after 0 weeks, right, how much money does she have? Well, she has what she started with, $450, right? We're told that. That's easy enough. I'm going to just maybe say 0 plus 450, or I could have just written down 450. There's really not much of a calculation there, right? Now, after 1 week, how much does she have? Well, we know at the end of each week, she is putting $15 into her savings account. So, I've done that only one time, but just to be kind of clear, that would be 15 times 1 plus 450, which would be $465 at the end of 1 week. Awesome, right? How about you pause the video now and figure out how much she's got in there at the end of 5 weeks, at the end of 10 weeks. And again, even though you probably don't need to, go ahead and write out the calculation. That'll help us kind of think about what our linear function should be. Pause the video now. All right, well, after 5 weeks, right, she will have put in 5 of those deposits of $15, and then she'll have that original of $450. We could figure out what the 5 times 15 is. It's $75, but we can actually do it all in sort of one calculation on our calculator. 15 times 5 plus 450 tells us at the end of 5 weeks, she's going to have $525 there. And likewise, after 10 weeks, that'll be 10 deposits of $15 plus the 450. So at the end of 10 weeks, we have 15 times 10 plus 450 gives me $600. All right, so just a little use of our calculator there. All right, so we've got now kind of a function, a very incomplete function shown in this table. Let's take a look at letter B. Use information given or from the table to write an equation for the savings S as a linear function of the weeks she has been saving W. All right, so now I want y equals mx plus b. But instead of y equals mx plus b, I want s, the amount of savings, equals m times w, right, the number of weeks, plus b. I think you have enough information to figure everything out there. Why don't you pause the video now and see if you can write down the equation for this linear function. All right, well, the plain fact is, right, the starting amount, 450, right, that is our b. That is our y-intercept. We can see it right here, right? When the input is 0, the output is 450. The slope, on the other hand, is the rate, $15 per week. So our linear function is s equals 15w plus 450. If you want it in function notation, and it didn't say you had to have it, we would write s of w equals 15w plus 450, right? Either one of these are fine. The function notation is particularly helpful if later on we want to evaluate how much savings she has after a certain number of times, which, again, there's letter C. Let's take a look at that. How much money will Janine have saved up after saving for 30 weeks? All right, well, that's kind of the whole point of our model. Use our model now to figure out what Janine's savings will be after 30 weeks. All right, let's do it. Simple enough, right? We're going to have s of 30. And this makes all the sense in the world, right? She's going to take $15 per week, multiply it by the 30 weeks, and then add it to the original amount of money that she has in there. Whoops. Man, I keep doing that. Grab my calculator, but move the text instead. 15 times 30 plus 450. She's got $900 saved up after 30 weeks. Excellent. Well done, Janine. Okay, let's take a look at letter D. If Janine saves for an entire year, what is the domain of this function? Use proper notation or describe the set. This is interesting. If Janine saves for an entire year, what is the domain, not the range, but what is the domain of this function? What kind of values could you put in for the input? Pause the video now and see if you can figure this out. Well, this is a little tricky. I don't want to use interval notation, and primarily because Janine is only putting in money at the end of each week. There really should be no fractional weeks that are allowed in this linear model, okay? In fact, right, she puts no money in, right? That's 0 weeks. We definitely can have that. But then 1, 2, 3, etc. So I claim that you should write the set out either like this. And how many weeks are there in a year? 52. So either you should write it out in roster form like this, or if you wanted to use set builder notation, you would say W is any integer such that 0 is less than or equal to W is less than or equal to 52. Now, of course, one of the premises of this problem is that you know that there are 52 weeks in a year. If you don't know that, then of course that kind of upper number is pretty confusing. Let's take a look at one last piece of this problem, letter E. Use the last 2 rows in the table in A to calculate the average rate of change of this function. Why does your answer make sense in the context of this problem? Okay, in other words, right, let's use these last 2 points, 5, 525, whoops, and 10, 600, to calculate the average rate of change of this function. Why don't you pause the video and go ahead and do that right now. All right, well, average rate of change, right, is always the change in the function's value, the change in how much has been saved, divided by the change in the input, the change in the number of weeks. So that's $600 minus $525, divided by 10 weeks minus 5 weeks. That's going to be $75 divided by 5 weeks, and that's going to be 75 divided by 5 is 15. Now, by the way, again, I always like to think about every part of my calculation, right? The change in savings divided by the change in weeks tells us, right, that we have saved $75 between 5 weeks and 10 weeks, right? And it took us 5 weeks to do that, and we end up getting 15, right? And why does that make sense in the context of this problem? It makes sense because Janine is saving $15 per week. In fact, had we gotten anything but 15 there, it would have had to have been wrong, right? I mean, the average rate of change of a linear function is its slope. So if we had gotten something like 25 there instead of 15, then either that would have been wrong or our answer down here would have been wrong. So this is just kind of a little check to make sure we're thinking about this properly. Let's keep going. All right, that didn't work. Let's try it again. There we go. Yeah, all right. Now, sometimes the information we have about our linear relationship does not include the starting values. All right, so in that last problem, which was really great, we knew that Janine started with $450. And the great thing about that was it gave us our y-intercept right away. Many times, though, all we know or all we are given is two input-output pairs that then allow us to find the equation of the linear function, right? Remember, a couple lessons ago, we spent a bunch of problems where we just took like two xy coordinate pairs and came up with the equation of the line. That's what I'm getting at here. Sometimes you have to do that even in applied problems. So let's take a look at exercise number 2. Lincoln is driving along a road at a constant speed. He is keeping track of how far he is from Denver. He knows that after 2 hours of driving, he is 272 miles from Denver. After 3.5 hours, he is 176 miles from Denver. Letter A, summarize the information given in the problem as two ordered pairs where the number of hours h is the input and the distance from Denver, d, is the output. Awesome. Okay, I'd like you to go ahead and write down the information they gave me in the problem as two coordinate pairs, and then we'll rejoin the problem. All right, what do we know? After 2 hours of driving, he's 272 miles away. So that's one coordinate pair, 2, 272. And we know that after 3.5 hours, we can handle some decimals. We've got our calculator here. After 3.5 hours, he's 176 miles away. All right, great. Letter B. Calculate delta D over delta H, the change in D over the change in H, which is equal to D of 3.5 minus D of 2, all divided by 3.5 minus 2. Include proper units in your answer. All right. Well, basically, I'm just saying take these 2 points and calculate the rate of change between them or the slope between them. Same thing, right? Pause the video now and see what you find. Now, we have to be careful here, right? I'm going to do 176 minus 272. Do not do 272 minus 176, right? Here we go. Delta D over delta H is 2, oops, and then I just about did it, what I said not to do. 176 minus 272, all divided by 3.5 minus 2. Now, I do want to point out something. You can do this calculation all at once on your calculator, right? Because you've got parentheses, you could just enter this as 176 minus 272, all divided by 3.5 minus 2. Okay? Hit enter, and I get negative 64. What are my units? Well, my units in the numerator are miles. My units in the denominator are hours, so that's negative 64 miles per hour. Huh, that's a little strange. Or is it? Let's take a look at letter C. You should have found that the average rate of change in B was negative. Huh. Explain why this is in the context of the problem. All right? So I want you to think about it, because obviously it seems like maybe Lincoln is driving at 64 miles per hour. So why is it then that we got apparently his speed to be negative. By the way, his speed isn't negative, his speed is 64 miles an hour. But pause the video now and see if you can explain why that slope is negative in the context of this problem. Well, it's pretty simple, really. If we look at this, at 2 hours, Lincoln is 272 miles away from Denver, right? I think it was Denver, wherever it was. Yeah, okay. And after 3.5 miles, Lincoln is 176 miles away from Denver. So his distance away from Denver is decreasing, right? His distance away from Denver is decreasing, and therefore the slope should be negative, right? In any linear function, if the output is decreasing, the slope should be negative, and if the output is increasing, the slope should be positive. So it's really simple, right? The distance to Denver is decreasing. So the slope is negative. Cool. All right, let's take a look at letter D. Assuming the relationship is linear, which it would be at a constant speed, write an equation for the distance d as a linear function of the number of hours h. So all right, we want to write the equation for this line, right, for this linear function. Now one of the cool things is we already have the slope. What we don't have is the y-intercept. So I want you to pause the video now and see if you can remember how you find the y-intercept for a linear model if you know the slope, and let's say if you know a point that lies on the line. Pause the video now and see what you can do. All right, well, what we do, whenever you have a puzzle and you know a piece of the puzzle, fill it in. So I know so far d is equal to negative 64 times the number of hours plus the y-intercept. What I don't know is the y-intercept, but I can take either one of these 2 points, and I'm just going to take the first one. I can take either one of those 2 points and I can simply substitute it in to this equation, which will allow me to solve for b. So now I'll do negative 64 times 2, which is negative 128, plus b. I can now add a 128 to both sides and move multiple things out of the way. And I'll find that b is equal to 400, I think. Let me just make sure of that. 272 plus 128, 400. And therefore my final model is d equals negative 64h plus 400. That's it, right? And this is exactly what we did a few lessons ago when we knew 2 points that lied on a line, right? And we know 2 points that lie on this line. We used those 2 points to first calculate the slope. We then put the slope back into the equation of the line and used one of the 2 points, and it wouldn't have mattered which. I just chose the one that didn't have a decimal in it. And we used those 2 points then to find the y-intercept. So now we have a full model. The distance that Lincoln is away from Denver is negative 64 times the number of hours he's been driving plus 400. Let's use that model a bit. Letter E. How far did Lincoln start from Denver? Justify. Well, it should be pretty easy. Pause the video now and see if you can figure out how far Lincoln started from Denver. Well, when Lincoln starts, by definition, by the very definition of what it means to start, it means that he's been driving for 0 hours. That means we're looking for the y-intercept, which is 400. Right? The y-intercept is the starting value. So obviously, Lincoln starts quite a bit away from Denver and is heading towards it. And of course, a good final question to ask in letter F, after how many hours will Lincoln arrive in Denver? Show the work that leads to your answers, right? So see if you can figure out how to use your model to figure out how many hours it will take Lincoln to reach Denver. Well, one of the cool things here is simply think to yourself, well, when Lincoln gets to Denver, what is the value of D? What is the value of Lincoln's distance from Denver when he's in Denver? Well, that's 0 miles, right? So we're really now going to just simply try to solve the equation 0 equals negative 64h plus 400. And that is a pretty easy equation to solve. I just need to subtract 400 from both sides, right? 0 minus 400, be careful there, is negative 400, which equals negative 64 times h. And now I divide both sides by negative 64. And we use our calculator maybe here. Negative 400 divided by negative 64. And that gives me 6.25 hours. And that's it, right? Models can be useful not only in predicting the output, but also predicting the input if we know a particular output. Okay, let's take a look at one last problem. Exercise number 3. A pump begins to fill a water storage tank when the volume drops to 225 gallons. The pump fills the tank at a steady rate for 150 minutes. After 60 minutes, there are 1,653 gallons in the storage tank, as shown on the graph. Letter A, what is the slope of this linear function? Using proper units, explain what this slope represents in the context of this problem. All right, well look, you've got 2 points that lie on this linear function. Therefore, you should be able to calculate the slope and come up with its units and come up with an interpretation based on the units. So go ahead and do that. All right, well, let me write out the 2 points a little bit bigger so we can see them. We've got 0, 225, and we've got 60, 1,653. Whew. All right, so my slope is going to be y2 minus y1, all divided by x2 minus x1. Let's bring out our calculator again to get that. I'm going to, again, do it all in one calculation. 1653 minus 225, all divided by 60, really, just at the end of the day. And that is going to be 23.8. 23.8, a little bit messy, that's okay. All right. Now we've got our slope, we now want to be able to interpret it, right? So explain what the slope represents in the context of this problem using proper units. Again, the units of slope will always be per unit, something per something. The units of the numerator per 1 unit of the denominator, right? Well, the numerator has units of gallons, right? I think that's it. Yep, gallons. And the denominator has units of minutes. So that's 23.8 gallons per minute, which means the tank, right, water is entering at a rate of 23.8 gallons per minute. Right? So we can tell every minute that goes by, that pump is filling up the tank 23.8 gallons. Every minute, 23.8 gallons, 23.8 gallons. Now, let's take a look at letter B. What will the volume be in the storage tank after 150 minutes? Show how you found your answer. All right, so like on the graph, right, we can see that after 150 minutes, we're getting pretty close to 4,000 gallons. The question is, what is the exact amount? Now, in order to do that, what you ideally want is you want the equation of this line, because that's what the equation will tell you, right? If you got an equation, then you can give it any input you want, for instance, 150 minutes, and you can get an output. Right now, we know what the slope of that line is, right? I think you should be able to figure out what the y-intercept of that line is, which means you can come up with an equation, which means you should be able to predict the output when the input's 150. Pause the video now and see if you can do that. All right, well, I think I'm going to use G for gallons and M for minutes. My linear relationship between gallons and minutes will be that the number of gallons is 23.8 times the number of minutes plus my y-intercept. And my y-intercept is sitting right there, right? The output when the input is equal to 0. Now that I've got this relationship, I can put 150 in for M, and I can figure out how many gallons I have. So let's take a look. G is equal to 23.8 times 150 plus 225. Again, we'll let the calculator do the hard work here. We've got 23.8 times 150 plus 225, and that gives me 3,795 gallons. Right? And that definitely makes sense with the context of the graph, right? I mean, it's tough because on the graph, the best I could do is kind of go, oh, I don't know. You know, it's something up there. It's between 3,500 and 4,000, right? Which definitely 3,795 is between 3,500 and 4,000. But the graph would not be the most accurate way of looking at this. On the other hand, this model can tell us exactly how much water is in there after 150 minutes. Okay, let's wrap this up. So a lot of what we did today was use skills that we had learned in previous lessons of this unit in order to model real-world phenomenon using linear functions, right? And the real key, always with modeling constant rate problems with linear functions, is knowing that the rate becomes the slope of the line and the starting value becomes the y-intercept. It's pretty much that simple. We're going to spend another entire lesson on this because it is so very important. It's one of the main things that you're supposed to come out of Algebra 1 with, which is a fluency with modeling constant rate problems with linear functions. So we want to make sure that you spend quite a bit of time on it. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.